My name is Daniel Thompson with Schneider Electric. I'm speaking on behalf of Current OS today. I've got a couple fantastic guests for us today. We'll be talking about DC distribution for the data center design and how we can present scalable power designs. With us today, we have Brian Deckard over the phone from Siemens. And we have Harry STOKMAN, who's Harry is co-founder, advocate, influencer extraordinaire. For those of you that are familiar with his work on the topic of direct current, should be no surprise. But we're just going to go through some housekeeping rules or housekeeping suggestions. So if you have questions, please put them in the chat, and I'll get to them when we get to our Q&A sessions. We'll be recording this session and distributing it out at the end of the session, so you'll get a link by email. Additionally, we'll post the video to the Current OS YouTube channel, so all of the webinar series for North American Webinar Series are uploaded there, and you can find them all there and watch them at your leisure. A little bit of an overview on Current OS for maybe those of you that might not be familiar. We're, I think, to 112 webinar session last week. And we represent 25 countries from around the world. So growing quickly, and we have all kinds of different stakeholders. The primary objectives of Current OS are to overcome the DC safety concerns and to simplify the stakeholders of the built environment by allowing for a multi-vendor system and interoperability, also boosting energy resilience and flexibility in the new landscape. A little bit about the organization. People have provided some questions after last session, so added this content. We have regular partner forums fortnightly. We have 6 committees and a couple extra task force that are dividing up the topics and allowing for the collaboration that we have across industry. And I think I'll maybe shed a little light on something that Harry said in our prep session for this session, that it's really a warm-spirited environment of collaboration amongst peers. So if you want to get involved, you'll be welcomed here. Of course, we take our learning through actual deployments of projects, and we look at those. This isn't just slideware. This isn't something that exists purely in a vacuum, but we're all learning together and sharing that learning and advancing that collaboration. So today we're going to be talking again about data centers, and I think it's important to index before we move forward in the session. And then we have good collaboration going on with the Open Compute project, and we have some similarities amongst our core values as far as efficiency, impact, scalability, openness, and sustainability. These are all sort of core values of both Current OS and OCP. So it's good to see that we're all working in the same spirit of collaboration. And with that, we're going to move on to our content, and we'll talk about system and product voltages, grounding and architecture, and our system of zoning and protection. And I'm going to hand over the first question we have today to Brian and talk about, why are we talking about this today, Brian? Like, what's the story behind this?
Thanks very much, Daniel. So, as you can see here on the screen, what we are witnessing is a significant and exponential growth of power usage, and also a significant increase of the percentage of that usage for data centers. What is not only happening is an increase of the power, but a need to actually consolidate this power into the compute rack for it to be able to perform optimally. And so what you can see over here on the right side of the screen is how there are different architectures of the compute rack, which have been contributing to an increase in the available power for that rack. You see the 3 bars on the left. This is more or less the trajectory of what is being achieved with AC. And then as you look over to the right, you actually see with the 𝗵𝗵𝗏𝗶, the DC architecture, and this tremendous scaling where really you're removing one of the key bottlenecks in terms of the traditional 50-volt distribution into the IT rack and going with a higher voltage DC first into the rack and then within the rack itself. On this next slide here, what you can see is these 2 stages of DC usage within the power incoming to the IT rack. And first, starting with a sidecar where the voltage incoming to the sidecar is still AC, but is converted over to DC and then utilized either at plus minus 400 or 800 volts for the IT rack. This is the Mount Diablo project for Open Compute. And then moving from there into a broader scope of power distribution, you have either the solid state transformer or other alternative forms of taking medium voltage AC and producing low voltage DC that can then power the IT rack. And an important distinguishing note about this particular slide here is the representation of sources on the left side as the system aspect of definition and product load characteristic on the right. And this is important as we look forward into the actual specifications for each, which are slightly different. You see a slightly tighter range of the source on the left is 400 volts plus minus 2.5% versus the plus minus 5% on the right with the product. And really key considerations here are that the AI load fluctuation can contribute to the ripple of the DC. And this ripple is important, as you'll see in some later slides, to the overall voltage margin. And as we increase the voltage up toward this 800 volt level, then there's great importance on ensuring that still some protection levels are maintained. And so really, this is a great opportunity for trying to have this ongoing dialogue between the data center community and the industrial manufacturing community in terms of what has been so far defined in a off-the-shelf type of approach for DC within industry or within commercial or even residential environments toward a very managed and specifically designed for application environments that we have with the data centers and their more tightly regulated voltage. With that being said, as we look at where we are today versus where the trajectory of things may be tomorrow, and in the extremely high roof line that you saw of where the power for the data center rack can go even beyond megawatt level, it's helpful to consider that with an AC system, typically you're increasing voltage by a factor of √3 between line to neutral versus a line to line. In the DC system, you have this instead factor of 2 between a midpoint. And this then becomes important if one could consider that there's the possibility to reuse at least certain elements of the design into the future in, say, a plus minus 750 type of scenario. So why does that matter? As you see in the yellow box, there are significant challenges which come into the picture for medium voltage in certain terms of additional design considerations, installation in terms of high voltage marking, trying to separate from the low voltage portion of the system, servicing in terms of tools and what they're rated and so forth. So one would like to try to avoid this. How does one avoid this? Well, in general, on the EU side, there's a low voltage directive which applies, and this is capping to 1,500 volts. And similarly, on the US side with the National Electric Code, the articles are scoped generally toward a 1,500 volt limit for the low voltage and beyond as high voltage. And there is an exception, an important one, which you see in the middle of the chart shown for 2,000 volts, but this is very specifically carved out for the solar environment. So in general, if one optimizes for the max power and voltage at the 800 level, but so tightly constrained to limit, say, to a plus minus 5% at 760 volts, well, then this could be somewhat challenging to extend further into the 750 volt space. And what could potentially more or less be some reusage of some componentry for a plus minus 750 volt application. Now, obviously, you don't necessarily get that extended range for free, so there can be some further power derating associated. So as you can see here, there is basically a split in the colored region of the middle of these two tables here. The table on the left is reflecting to the actual voltage bands with B numbers and the reaction times associated to those bands. On the right, what we have represented is the actual voltage levels, these U numbers. And the important thing here being that the current OS band, which was set up, which is having a nominal, you see this UNOM, I guess the third line up as 700 volts, is in general sharing a lot of characteristics similar to the 𝗿𝗂𝐴 region, as well as also at the half volt level to the 𝗵𝗵𝗺𝗃 and 𝗵𝗁𝗃. And this more or less did not happen by accident. This is an intent, and this is also reflective of the characteristics of components, starting with the semiconductors and the class in which you are specifically trying to optimize for. So one key takeaway, though, from this particular slide is that if you notice the green happy region of operation, which is from U2 to U3, is actually coming in below the 400 or 800 volt level. That is actually constrained to 10 minutes of operation, 600 seconds there. And so then the question, came, how can we actually proceed forward to utilize what already exists and to be able to build on? So here, as you can see in the middle graph, we have typically a set of items, be it the load ripple, the voltage ripple associated to the distribution, the source swell, and the source ripple itself. And these all more or less form the system tolerance which exists between that continuous range of operation up to the very important U5 level. If you look to the chart, you see that above U5, you have an important characteristic, which is the characteristic of the TVS curve in yellow. And what happens there is that you, above this U5 level, have significantly increased conduction. And so it's very important to maintain what you see as the margin labeled right above that triangular peak to that U5 level. And as we raise up this this nominal voltage, then obviously that margin significantly shrinks. So with that being said, we have to apply a slightly different approach than what has traditionally been used. So here I try to put in perspective as the analogy to where many are probably more familiar on the AC side. So on the right, you have an example of a IEEE 1547 definition for distributed energy resources. Here was just taken specifically category 3. There are other categories. There are specific regions, for example, above the green, you see the orange, and this is a momentary cessation region. This is where a distributed energy resource should actually not produce additional power and apply that into the circuit. This is to protect from the orange, the darker orange or red region beyond, where there could be damage to equipment if you are spending too much. Certainly, even at the orange region right above green, there's also this possibility. So, with that being said, this is actually quite analogous to what we are dealing with for moving from what you see in the middle as the 𝗖𝗄𝗏 TR63282 Table 1 based system and product definition, where there is a differentiation, if you notice, between the product and the system on the B2 yellow region. This differentiation is to accommodate that you may have distribution-related losses, and so you need to support a lower voltage at the end, where you have your actual equipment separated by distance from the source. Here, though, on the managed aspect, as you notice, we have kept the anchor points on the low side, but we have changed the operation underneath the anchor point of the B6 band on the high side. And literally what we have done is to consider that similar as what you saw on the earlier slide with the OCP definition being tighter in tolerance on the Mount Diablo power rack versus to the power shelf that was in the IT rack having a slightly extended further range. In this way, you try to ensure the overall maintenance of that B6 band and the U5 level by trying to reduce first at the source, continued the operation with the load all the way up to that level. Here, what we have done is, again, capture a different behavior in terms of the system versus the product of those columns where you have 800 and 820 versus 800 and 840. And what we then do, as you see in the yellow box at the bottom, is to consider that the B4 band has been increased in time from 10 minutes to indefinite amount of time. And therefore, since that indefinite amount of time, we need to make some additional considerations when coming to 1500 volts. At the moment, we as you see in the proposal draft, put out a potential to maintain that 2.5% source tolerance underneath still the 1500 volts low voltage threshold, and at the same time extend beyond from the product perspective to somewhat further, which is actually reflective of what we see in standards as well, that typically in use you may have a product which is rated for a higher voltage as a load than you're actually using in practice. So here you have an example of a power supply. And this particular power supply has a voltage rating of 100 to 240 volts. And it does not show on the actual label, but it does show the particular standard, IEC 60950-1. Applying that standard, gives you a slightly wider operational range of 90 to 254 volt. In a similar way, we look at the topic of, as you see on the far left picture, taking, say, the plus minus 5%, applying it to a 100 kilowatt power shelf, and considering that this can go between 760 and 840 there. And then further, if you were to reduce in voltage, you would not necessarily need to just cut off power, but you would actually be able to just derate in power as you see the power levels going down, and those power levels corresponding to what is possible at that voltage given the fixed current limit of what you've designed that component for. So with that being said, you could imagine that it's possible to, say, design for international use. I mentioned on a previous slide, but didn't in the text, but didn't highlight that, for example, preferred voltages within China are, say, plus minus 375 or plus minus 750. So if you wanted to support that fully, you can see here that by increasing the current rating of the component by 9 amps from 131 to 140, then you would be able to still support full power for that particular voltage. And then you can imagine with the curve and the rate that if you wanted to support the full range of what is typically within the current OS band, going all the way down to 640, this is also possible. So with that being said, this is also an important aspect for the ability to handle topics like black start and so forth, that you have this typical full usage of the band. And if you did implement a droop curve, say for the situation on the left where you don't want to actually operate below a certain voltage, this could certainly be achieved, and you could reduce that power down to zero at the appropriate voltage. And this would still be possible.
We have different architectures that we embrace when we start looking at how these systems come together. They're really sort of splinter off from solid grounding. So you can see the TN, the TNS for the grounding conventions. It's more of a European terminology in those grounding systems, but we can see that. I'm getting a note too on the chat that we can hear Harry.
Okay.
But I can't hear Harry.
Okay. No. Okay. Now then I continue on the earthing, because the earthing is a very important topic. And Daniel, you explained perfectly the principle of the AC side earthing, that earthing and AC and DC have a similar kind of topology, except we don't use TT in DC and we don't use TNC in DC, because this has a very big drawback in the architecture to use. So here you see the possibilities for DC side earthing. So you have a 3-wire system where you can have a high impedance. So if you go to the left top, you see an IT system that is isolated. That is where the 3-wire system is floating. This is, by the way, this is an incredibly complex structure to use, because you have a lot of spacing considerations to take in the equipment. And below that one, you see the TNS version of a 3-wire system. And what is important to understand is that when you go to the Unipolar version, then you see in the third column, you see two architectures up and below each other. So that means in the case of OCP, you can have, for example, 800 volt against PE. So you have a positive, and you can wire it in a negative way, and you have a minus 800 volt. But if you combine it with the picture on the bipolar and the 3-wire system, if you look to the left, then you have a full bipolar system. So what is interesting from this kind of architectures, and that is what we want to highlight, is that if you have to define products that are connecting to these architectures, you can do it in a smart way. You can design your product to be suitable to withstand 800-volt against PE. You can design it to withstand minus 800-volt against PE. And you can, of course, then you can use it in a 3-wire system. So you can then be future-proof and you can go to the maximum voltage that you can do in the low voltage domain. But that means that you can use this equipment also in IT systems. I think this is an important message for product manufacturers of these devices, because in the end of the day, maybe some data centers want to use, have strong reasons to use an IT system. Some other data centers want to use a TNS. And if you define the product in a proper way and you define them to work in unipolar systems, then you can always use them in bipolar systems, in IT systems, etc. And this gives this wide range. And this is a way to decouple the products to withstand any possibility. So here you see it a little bit. And in 𝗏𝗏𝗏𝗏, we have the first picture we don't use so much because it's incredibly complex. And we don't have live experiences, physical experiences with this type of architecture. That's why the reason why we support it, but we don't promote it. And the picture below, you see the 3-wire system with the TNS. That is tested, that is used, it's built. We have validated this structure, it's working. We use it for certain applications, but we technically we recommend for particularly for OCP, we like to use the 3-wire system because 3-wire systems is still complex, particularly when it comes to multiple sources. Then it becomes a little bit complex because you need to manage the currents in the midline. So you see the 2-wire IT. That one is suitable to build, suitable to use, and can be recommended in certain applications. It's not fully described yet in 𝗏𝗏𝗏𝗏 because we don't have enough reference cases that are built in this way. So of course, we know in theory and we know from lab situations how it works, but from real life applications, we don't have enough experiences on this one. And that is the same for the 2-wire with the floating midpoint. It's a similar structure, but again, it's similar like the first one. And then you have the midpoint earthing. That is the fourth picture. And this is also complex, not really validated by 𝗏𝗏𝗏𝗏. And then we have the 2-wire system with an earth midpoint that is covered by 𝗏𝗏𝗏𝗏. It's also covered by ODCA. It's a possibility, but it's limited to a single voltage to use. So that means you can choose to operate on plus or minus 400 and use this equipment in 800. It had a big advantage that the spacing requirement is only 400 volt. But that means if you want to use the same equipment in the IT version, then you need to go for 800 volt insulation to PE because you can have earth fault and the equipment must withstand 800 volt. So this is important to know. And here, this is the one we really strongly recommend in 𝗏𝗏𝗏𝗏. The reason for that one is that the positive system has the most simple architecture to build an installation with distributed sources. And imagine an OCP, because when you have a cable that is going to several racks, it will be most likely possible to power it from the other side. Or if the racks start to grow, the systems start to grow, maybe you want to go to a multi-port, multi-source system with multiple points of feeding the system. And if you do that, then this architecture is the most simple one to use because you can easily run islandable. You have single pole protection. And what is also important to understand is that these architectures have positive effect when you have to deal with stray currents. And to give an example, because the picture below you see, for example, a negative system. In the telecom, it was quite common to use minus 48 volt to connect to equipment. And that is mainly done because you want to prevent corrosion effects on the L minus, on the electrical installation. But that result that you could have some corrosion effects in the structure, in mechanical structure. And if you go to the first one with the positive system, with the positive voltage, that means technically you could have corrosion effects on the L+, but you have less risk of corrosion on the structure. And think about it in OCP, because you want to do immersed cooling, you want to have a lot of earthing arrangement to do, you have a lot of piping, so stray currents can be quite dangerous because they could have effect to the equipment. And if you take and that the architecture with the positive system is the one who has the most the lowest amount of drawback on these kind of effects. And this one is another architecture that is the non-isolated converter. And then you have the two voltages against PE, so you have a symmetrical system. This sounds easy, but this has drawbacks. This is not completely validated in current OS, but this is validated in ODCA, and it's mostly for industrial use. The big drawback of these kind of architectures is that you have a lot of EMI in the system that is distributed through all the power racks. So you have there to do. And it is very difficult to scale to higher voltages because you are linked to the mains. Brian, you want to take over, or do I continue?
Yeah, no, I'll take it here.
Okay.
All right. So here you can see a representational diagram of different zones which are applied. These different zones are in order from low to high of increasing protection. So at zone 0, you do not have protection. Zone 1, you have some means of protection. Zone 2, for example, as you see, the solar panel in the middle top of the diagram is typically like a current limitation, which can be assumed. In zones 3 and 4, you have ultra-fast semiconductor protection. The difference being that zone 3 allows for multiple sources, where zone 4 is focused on just a single one. And the key point here is that zones 3 and 4 simplify the design and restrict the bulk energy. As transition to the next slide here, as you can see, the key points which I want to highlight out of a lot of text here on the slide is that for the columns DC zone 3 and 4, in the middle there is the comment the incident energy is very small, less than 1.2 joules per centimeter squared. And this is certainly important from perspective of the arc flash topic, which I would show here on the next slide, that in general, the AC side of the arc flash topic has been studied in greater depth for a longer period of time than the DC side. There is some guidance within 7DE. There has been some recent work toward trying to be able to further revise that guidance and to make sure that the right level of incident energy is calculated for the conditions. So with that being said, recently we actually had at the first North American General Assembly of Current OS in Cleveland, a workshop on this particular topic where key experts from the historical 1584, as well as specifically also from the DC focused aspect of the 𝗏𝗏𝗃 topic were involved, and we had a very engaging discussion and are working to define further the next follow-up steps from that. So in general, for the next steps, there is a lot of collaboration, which is really multiplying the effect of the effort here. So we have presently a 2026 NEC that even has not fully crossed over into the effectivity, but already we work on the one which comes after, which is 2029. And from that perspective, there are a couple of task groups for direct current and data center, where we are looking specifically at the topic of DC and what could be areas to refine within the National Electric Code. Also, just continuing to go down this page here within NEMA. Similarly, there's a direct current task force underneath codes and standards, focusing to the more general topic, while there's also a data center work group within high performance buildings, focusing on important differentiators for this managed application, be it the 800 volts or the potential extension of that, etc. So with that being further said, as mentioned earlier, we were able to include the Fire Protection Research Foundation from NFPA into the 𝗏𝗏𝗃 workshop that was held in Cleveland, and continuing discussions toward identifying the appropriate test plan, considering the timeline that we have toward being able to influence the 70E standard there. And further, from the UL perspective, there was recently a data center power summit, which included a number of participants, both from the data center side as well as in general, specifically companies that are very involved in this topic more broadly of direct current. So further to that, there's a UL 3001D specific set of meetings to create the equivalent to UL 3001, which was just recently released for AC, distributed energy resource systems, only the DC equivalent. And then over here on the right, what I'd very much like to highlight is that topics such as the voltage level, the polarities in system earthing, protection, etc., are very much being expanded upon in an environment that enables all to openly contribute and accelerate this effort, given the timelines that we are up against for the rollout of DC in the data center. So there's specifically Open Compute project which has been opened, and you're very much encouraged to join us there for that effort. Moving to one of the final slides here for the data center presentation, I want to thank all of the participants that have really put a lot of effort in a short amount of time to try to prepare this presentation, these materials, and really to advance this important application of direct current. And that actually brings us with 15 minutes left to Q&A time. So,
Sharp timing.
Be able to.
Yes, I saw one question from Karsten about the B2 band, that the -30 is not requiring too much oversizing. Of course, if your use case is running full power on the whole band, yes, then you need to oversize the band. But if you take the current west and you can apply, for example, reduction of loads, because you're running maybe in a 𝗿𝗁 case, and this band is actually meant as some kind of critical band, and that means when you have normal operation, for example, in the range of 800 volt to power your racks, and for some reason you have maybe an outage, and you have still batteries active. The batteries have maybe a limited amount of energy. So if you don't want to stop computers, but you want to continue kind of some kind of services, then you can, for example, the unnecessary loads, you can discriminate, and then you can use the smaller loads to continue to supply. So that is actually the mention of the B2 band. And the B2 band has also technically another effect, is that normally the band in between U2 and U3 is normally a band that is current controlled because it's running on droop, and B2 can be voltage, constant voltage. That means if you run in a kind of instability in your system, then maybe your system start to oscillate, for example, that can be a possibility. Then the B2 band prevent that your system will collapse. So it is a very important band to keep the system active and to give the possibility for the system to recover in a case you run in an emergency case or in a critical condition. Is this answer your question a little bit, Karsten? Yes, and I see in other questions that the bands are meant for many multi-source operation. Yes, and that's maybe also to explain, because you can never connect constant voltage sources in parallel, because that will be impossible, because you get very strange currents in that case. That is the reason why you need to have a kind of droop between the sources. So every source anyway, if you want to operate your system, for example, at a fixed voltage around, for example, around 800 volt, and you want to parallel sources, you need to have a kind of droop between the sources to have equal current sharing. And in current west, because in current west we have a very open system that is meant for many, many different use cases, not only data centers, but also buildings, other applications. And when you have long cables and when you have multiple sources feeding into the system, then you need to widen the band a little bit, and then you can use this multi-source environment. And if this band is too small, too tiny, if, for example, if you take only 10 volt and you have a big system, then you get a kind of constant voltage effect, and it's very difficult to use distributed sources. And are there more questions?
Yes, there was an additional question on what are the advantages of M to L-. I think you said less corrosion with L+ to M. This is from Cheyenne.
Yes, that is a huge difference, because from a corrosion point of view, a current, positive current entering in the structure, if you're using on boats, you will have normally anodes, and these anodes will introduce a positive current to the structure to protect the structure against corrosion, while the negative current will make the structure what we could technically call anodic. So that means if you have a symmetrical system and you have a positive line and a negative line, from the system point of view, it looks like that these currents are canceling out and it's not an issue. But from the corrosion perspective, a positive current is less dangerous than negative current for the structure. So the negative current will dissolve the structure, and the positive current will create some corrosion on the terminals, but not corrosion on the structure. And what is important is that the terminals of the electrical installation can be inspected, but the structure, the metal structure, the cooling system, etc., is very difficult to inspect on these kind of effects. So from the corrosion point of view, the electrochemical reaction, it's a huge difference if you talk about L+ and M, or you talk about M and L-. And advantage for systems, in particular when you have this mixed environment with high power and water cooling and piping and all these kind of things. Then an L+ and M is makes more sense from the corrosion perspective. And are there more questions?
Yeah, no, thanks very much for that explanation. I'm looking through this list and I'm not seeing any additional questions at the moment. So I'll put out the call again. If there are any further questions, please add them into the chat. We would love to talk further about those.
Okay, no more questions, looks like.
Oh, we just got the additional one. What about supercaps for UPS energy storage versus lead acid or lithium?
Oh, that's a good question. This is a difficult one. Because probably you want to use the supercaps to manage your loads to avoid, to reduce the peak load from the ripple. But supercaps are so aggressive, they are very hard to connect to a system, and they need a lot of functions to charge and to synchronize. So they looks like batteries, parallel batteries on the system. They need to have a kind of management system. And while capacitors are quite easy to do, and technically, it's very complex to use these components directly on the distribution system, because they will add a lot of chances for protection on these kind of systems. So most likely they will be probably used in combination of a converter, so that the battery or the supercap is behind the converter, and the converter controls the voltage on the bus to manage the peak load. So again, that is working on the droop to make that happen. So, and technically with supercaps, you can of course have very high C rating of charge and discharge. It's limited in energy, but it has a lot of power. So it is like in AC, you can compare to like a flying wheel. And so it is power storage and not so much energy storage. But I think they are needed in this OCP data center, because the load dynamic of the load is so big. And if you do that on this high power level with such dynamic loads, yeah, it will be very hard for the distribution system to get not to create so much voltage deviation in the distribution system. And that's why probably it will be combination. And we expect that these supercaps are behind the converter, very, very close by the power rack. Oh, the IT rack.
And maybe I just quickly add that I've already also seen some further dialogue about this topic starting to kick off within the OCP work streams, that there's very much a desire to have greater ride-through support for large loads, and that then how this cascades down at the different stages of energy storage in the gray space and the white space, etc., is something that is being very actively looked into by key hyperscalers in this type of, let's say, requirements type of development. And then certainly we want to look at how the characteristics of what we are implementing with the voltage bands and reactions and so forth can best support this type of desired grid support behavior. So.
Okay. Yeah, I think that were all the questions.
Okay.
Oh. A new one.
We got one more. In the architecture, which type of protection do you use in case of the TN? It says SC in load side. I'm guessing they mean CS.
Yeah, I think if I understand the question well, I think technically, I think for
sorry. My bad.
Sorry, Brian. Maybe you want to answer it.
Yeah, no, I don't want to, but I did want to just clarify that I misunderstood the question. It was in the architecture type, which type of protection do you use in case of short circuit in the load side?
In the load side, so in the inside. Oh yeah, there's then technically I think you depends on the size of the load, how the converters is built. If you have many small converters in parallel to make the 50 volt for the CPUs, I think then you can probably use fuses to protect the internal faults for these kind of converters. Because if you have a distribution system, not a sidecar, but if you have a distribution system and you have many IT racks on the same system, then the power on the bus is incredibly high. And that means that the fuse is still small. So when you have overload or internal short circuits, then probably the fuse can be easily used to trip the fuse. And the negative effect of blowing the fuse, like the voltages, is in this case eaten by the system. It will be different if you want to use this kind of protection at the source side, because then you can have very nasty effects. But on the load side, you can use kind of fuses to save cost and to have protection of the equipment itself. And most likely, it should be technically internal fuses, because if your fuse trips off the load, then you have an issue on the product anyway.
Really quickly, because I know we have 3 minutes left here, maybe I take this last question that's in the chat as a segue toward, again, the 𝗍𝗶 further effort. It states, do your data center protection strategies include intertrip schemes or dedicated arc flash mitigation systems, and are there any additional measures you consider essential? So there is an intertripping wire scheme which CurrentOS uses with multiple sources. And the behavior of this could be different in case of, let's say, global type of problems versus specific to a particular source that would not impact the rest of the circuit. And so we're happy to dive further into those topics within the 𝗍𝗶, as well as specifically looking at the arc flash considerations. What are the benefits of Zone 3 and 4 solid state protection and so forth, but certainly considering as well other effects like current limiting converters, etc. So with that, I will go ahead and advance to the next slide here, which is an invitation for those who are able. We would love to be able to have you as part of the upcoming CurrentOS plenary, actually the 10th in Lisbon, Portugal, there on the 29th and 30th of January. We had an open invitation as well to the recent Queensland General Assembly for CurrentOS, and it was great to see a lot of new faces, and we very much look forward to hopefully meeting you there. And with that, let me go ahead and advance to the final slide. That is a wrap, and we are at 1 minute before. So thank you all very much for your participation, the great questions. Look forward to following up together and continuing this effort within the 𝗍𝗶 power distribution space. Thank you very much.
Okay, yeah, thank you all, guys.